Good morning. I assume that you can hear me. Can someone verify that sound works well? Okay, thank you. Thank you for the verification. No. My name is Andronikos. I'm Andronikos Paliathanasis. I work in Chile, and this period of the year I'm visiting Stellenbosch University and NITheCS through NITheCS, and I would like to uh, have this mini course and present you some basic applications of the symmetry analysis for differential equations and in physics, in physical science. And actually, in this mini course, I would like to give the basic properties and definitions for the concept of symmetry analysis. And I will present you today some applications in classical mechanics. And the next week, we will extend the applications in more problems, either from quantum theory or in fluid dynamics. So, the plan of today's course will be, firstly, I will make a small discussion about the understanding the symmetry, the Newtonian world. Then I will present you the mathematical definition for the symmetry, for the concept of symmetry. And then I will talk about the symmetries of functions, the symmetries of geometric objects. Later, we will discuss the extension of the symmetries in the case of a jet bundle. So we can go to the case of differential equations. I will discuss the case of ODEs, but they can be extended next week. We will extend it easily on PDEs. Then I will show you some applications where we can use the symmetries to construct solutions for physical problems or conservation laws. And of course, I will give a short discussion on Noether's theorem. So I will go slowly. I will be happy if you have any question. You can write me or interrupt. It will be nice to make it a discussion. So initially, in the symmetry in art, we have the concept of symmetry in art. It's an expression of invariance at some form of translation, rotation, or reflection. Where, I mean, I'm sure you have the tiles in the floor. You can see that the tiles are placed with a way that they have what we call a pattern. And this, this pattern is symmetric, either way you move from one direction to another. It is interesting when the tiles, for instance, are not straight aligned. Our eyes observe it immediately, and this seems to be not calisthenics, not nice to our senses. A big example of symmetry of tiles is, I mean, we have the Arab tiles, the Arab architecture, where there it's very clear the expression of the symmetry in art. In modern art, in modern buildings, we have, we have repetition, we have a symmetry, we have a reflection. So as you can see, the concept of symmetry in art is very important. In science, the concept of symmetry appeals for this leads to a characterization of the system under consideration. And the invariance associated with the symmetry produces a simplifications which makes understanding easier. Now, to take a simple example, I will be Newtonian today. We consider the Kepler-Coulomb problem in reduced coordinates. It's described by the equation of motions given by the second-order differential equation. A dot, as a physicist, a dot represents a derivative with respect to time. Now, me is a constant and it's related to the mass of the mass applied to the gravitational law. An over dot denotes differentiation with respect to time. And we know that this equation is invariant under translation and rotation. We know it's a central force system, so we know that under rotations, the system remains the same. Now, the associated invariants are the energy and the angular momentum. And when the quantum mechanics analogous is examined, the spectrum of the energy operator is found to be more degenerate than the conservation of angular momentum will imply. Moreover, the equation is invariant under the similarity transformation. If you apply this transformation in the equation, you will see that it is invariant. Well, A is a parameter of the transformation. It's a constant. So this similarity transformation leads to this property that r cubed over t squared is just constant. This is nothing else than the Kepler's third law of motion. So in this mini course, I would like to show you how we can derive this similarity transformation for the Kepler's problem, and I would like to present you actually the systematic construction for this approach. Now, symmetries can be categorized in discrete and continuous. For example, discrete symmetries can be found in the transformations which leave an equilateral triangle invariant. If I is the original orientation of the triangle, then a rotation of 120 degrees in a clockwise direction by r, the same triangle is found after the application of r. R squared r cubed equal I. So I mean, when we have a triangle, equilateral triangle, we rotate it around 120 degrees, we get the same triangle after 3 times. Where a threefold application of r is the same as the identity. The anticlockwise rotation through 120 degrees reaches r minus 1. That means that r minus 3 equal to I, while r minus 1 multiplied by r equal I, and etc. This means that we will rotate the triangle once on the clockwise and once anti-clockwise, we get the same triangle. These rotations actually form what they call an abelian group. Now, the equilateral triangle is invariant in the rotations of multiples of 120 degrees about an axis normal to the plane of the triangle through its droid. Some combinations of reflections with reflections and rotations for the equilateral triangle. On the other hand, now we will move to the concept of continuous symmetries. On the other hand, for the circle, rotations by any angle about an axis normal to the plane of the circle through its center leaves the orientation invariant. In a standard representation, a rotation through an angle theta, so that at the point P with coordinates x and y moves to point P bar with coordinates x bar, y bar, is given by this transformation. This is a continuous transformations that can be considered as succession of very small transformations from the identity. As you can see, this is a clear transformation that we know that is a rotation in the polar coordinates, in Cartesian coordinates. Sorry. Now, if the angle that we rotate is extremely small, and we expand around theta, we assume that theta is epsilon, where epsilon is very small, and we expand around Taylor expansion near to epsilon equals 0, then this transformation can be expressed in a very nice form, simple form like this. Where we applied, where the standard approximations give for epsilon very, very small, that the cosinus of epsilon to be 1, and the sinus of epsilon to be linear to epsilon. The finite transformation may be obtained by integration of the following system. So from here, we can construct a system of differential equations, which we can solve it with these initial conditions and construct the original system. So we have a finite transformation and infinitesimal transformation we can construct by solving the system F and continuous transformation, infinite transformation. Now, I would like to be a little more, I will try to be actually mathematically solid and correct. So now we'll discuss mathematically the concept of symmetry and how we apply it, how we define it. So if we assume that we have a manifold M of class CP, which is smooth and nice, and U be a neighbor in M, then we consider that we have 2 points P and Q in the region of U. With each one, we have coordinates xp, yp, and xq, yq, respectively. A point transformation of U is a relation among the coordinates of the points PQ over U, which is defined by the transformation equations x prime q is given by this, where the functions indeed are CP minus 1, and the transformation has the same property, which means there is an inverse. And variables x, y are independent. A special class of point transformations are the one-parameter point transformations. Now, which are these transformations? The one-parameter point transformations, 1 PPT, are point transformations that depend on arbitrary parameter as follows, where epsilon is a real number, and the transformation satisfies the following condition. The transformation is well defined. That means that if x prime for point x1, y1 is equal with x prime for point x2, y2, and etc. for the y, then necessarily x1 equal y1, x1 is equal x2 and y1 is equal y2. There is a typo here, sorry. The transformation that can be composed, the transformation is invertible, and there is the identity transformation. The 1 PPT for a group of one-parameter point transformations defines a family of curves in the manifold M, which are parameterized by the parameter epsilon and are called the orbits of the group of transformations. These curves may be viewed as the integral curves of a differential vector field X, which belongs to the manifold M. So these vector fields that we will define now, it's the vector field that will be the generator of the transformation, and it's the vector field that we will call as a symmetry. Now, let's x bar, y bar be the parametric equations of a group orbit through the point P. Then the tangent vector at the point P is given by the following expression. The vector xp defines near the point P a point transformation of this form. This is an infinitesimal transformation where we have set C P to be this component and eta to be defined by this. This 1 PPT is called an infinitesimal point transformation. The vector field X is called the generator of the 1 PPT along the orbit through the point P. Evidently, the infinitesimal transformation moves a point along the orbit of the group through that point. Now, for the example that I presented before, for the rotation, so the transformation for the rotation in Cartesian coordinates is this one, and we can calculate the vector field of the generator for the infinitesimal transformation. So, C is given by the partial derivative of x prime over epsilon, and for epsilon very close to 0. So if we take the derivative and we take epsilon to be 0, we get that C is equal minus y. With the same approach, if we take start from eta for x and y, then the partial derivative of y bar with respect to epsilon, when epsilon equals 0, is equal with x. From which follows that the generator of the infinitesimal transformation is x to be minus y theta x plus x theta y, which is the rotation of the Euclidean space. It's nothing else than one of the three symmetries of the two-dimensional space. Now, let us now consider a function f to be a function in the manifold f with a value, a specific value at each point p. Then, under the one-parameter point transformation, the x and y will change to x. We will go from point p to point p bar. Then the function has a value f bar at the point x bar, y bar. Since we were in a point and we move it to another point. Since x bar, y bar changed, we assume, logically, the value of the function will change. Now, the function is invariant under this is the definition, it's invariant under the one-parameter point transformation if and only if f bar, the value of the function of the point p bar, is 0, when the value of the function of the point p was 0 at all the points where the one-parameter point transformation acts. That means that if the value of the function remains the same under the application of the one-parameter point transformation, then the function f will be invariant under the action of the transformation. Equivalently, the generator x of the point transformation will be characterized as a symmetry of the function f if the action of x on f to be analog of f lambda times f when modulus f equals 0. So this is a mathematical expression, and this is what we'll use to construct the symmetries later for functions, geometrical objects, and differential equations. So as you can see, the definitions means that the functions will remain the same. The value of the function will remain the same at each point where they are related through the transformation. Now, the symmetry condition, this is called the symmetry condition, is equivalent to the following system of first-order PDEs. The action of x, of the operator x on the function f to be equal lambda times f, or we can say 0. The characteristic function or zero-order invariance w of x is defined as follows. So this is a characteristic invariant of the transformation, and this has the property, this characteristic invariant has the property that when x acts on w to be identical 0 by definition. Therefore, if we were able to write a function, therefore, if f is invariant to x, then there exists a set of change of variables where we can write f in terms of the invariant function. And w is a zero-order invariant which satisfies x as a symmetry. Now, let f, so we define the concept of a symmetry. This is x is a symmetry if it leaves a function invariant, and w is the characteristic of the symmetry vector. Then, if a function is invariant under a specific symmetry vector, we can say that we can see that the function can be expressed in terms of the invariant function. Now, if f be a function m, which is invariant under a multi-parameter point transformation, not just one parameter point transformation, but can be invariant under a multi-parameter transformation, which the multi-parameter transformation can be described as a set of m one-parameter point transformations. then F is invariant under M infinitesimal generators. That means that the function F admits M symmetry vectors. The symmetry vectors form a Lie algebra. A Lie algebra is a finite-dimensional linear space G in which, with a binary operator described by the Lie bracket, the commutator, and has been defined, which has the following property. The commutator of x with respect to itself is 0, give us 0, for x belong to the group, to the G, the space G. Then, if x, y, z are 3 of the symmetries of the function f of the same group, then they have this property. This is a Jacobi identity, and this property actually indicates that the vector fields, the transformation, the space has, it's a flat space. I will tell you now how we interpret that. Now, if xa and xb are two components of the vector of the linear space G, then the commutator of xa and xb is given by C capital, CAB are indices, where C, CAB are constants and are called the structure constants of the Lie algebra, which are antisymmetric. Now, if we define C as a connection of the derivative, since the bracket, it has a property to be a derivative, then the property 2, the Jacobi identity, can be seen as a definition of the Riemann tensor for the derivative for the bracket. So that we can say that we can do the analogy from Riemannian geometry that the linear space G is a flat space. Okay, this is the definition for the commutator. As I expressed now, is defined by this, and the structure constants satisfy the identity. The structure constants, the derivation of the structure constants is essential when we have a specific Lie algebra, since they characterize the Lie algebra because every set of constants defined locally and uniquely grouped. The structure constants do not change at the coordinate transformations, however, do change at the transformation of the basis. This property, the last one, is essential because it can be used to simplify the structure constants of the given group. And we will use this later in an example. Now, I will give you another one definition, and I will move from the concept of functions to the concept of geometric objects. Consider an n-dimensional space in a smooth manifold of a class CP. A geometric object of class R, it has the following properties. In its coordinate system, it has a well-determined set of components. I want to make clear now, maybe I didn't mention before, I had to make it clear here, that I use the Einstein summation. So when you see CC here, one upper and lower indices, I consider sum on this. Now, under the coordinate transformation, the coordinates of the geometric objects in the new coordinates are represented as well determined functions of class R prime, where P equal P minus 1, of the old components of the function G, J, which we see how they're defined, and of the S derivative, that is, the new components of omega prime of the object, can be represented by equations of this form. Function, where function phi, the capital phi, it is a map, it's the function that relates the geometric object omega with value at the point x, p, with the geometric object omega prime of the geometric object omega prime with values at the point p prime. So functions phi, the map phi, have the group properties. Now, which is this is the definition for the geometric object. This is explicitly the definition of the geometric object. And now, in order the coordinate transformation, the law for the coordinate transformation defines a geometric object, characterizes the nature of the geometric object. A specific class of geometric objects are those which have a linear law for the transformation. Indeed, the phi could be a linear function in terms of omega given by this expression. This is a Jacobi matrix, and C it's another component term. When the transformation law is of this form, we shall say that the geometric object is a linear and homogeneous geometric object. One important class of linear homogeneous geometric objects are the tensor fields. A tensor field, it is a geometric object with this law of transformation. When R is equal to 1, the tensor field is a vector field. When R is equal to 0, the tensor field is a function. When R is equal to 0, we have a second rank tensor field, etc. It is important to observe that since J is a Jacobi matrix, that if a tensor field has a specific 0, for instance, has component 0 in a specific coordinate system, then it means that either in every other coordinate system, its value will remain 0. However, that's not true for other linear geometric objects which are not homogeneous. Consider, for instance, the connections in the for Riemannian manifold. To do that, assume the equations of motion for the free particle in Cartesian coordinates. We have the equations for the two-dimensional free particle to be x double prime equals 0, y double prime equals 0. However, if we move from Cartesian coordinates to polar coordinates, then we will see that we know that there appear some components which are quadratic on the first derivative. These components are related to the connection and specifically they are followed from the transformation law for the connection, which is a non-homogeneous linear transformation. However, the space remains flat, either in each coordinate system. However, the connection is has not 0 components. Now, as in the case of the functions, a linear differential geometric object is invariant under a one-parametric point transformation if and only if omega bar is equal to omega with values at p and p bar at all points where the one-parametric point transformation acts. Equivalently, the lead derivative of the geometric object omega with respect to the infinitesimal generator x vanishes. That is the lead derivative of x on omega, where Lx equals 0, Lx is a lead derivative. The definition of the lead derivative depends on the nature of the geometric object. When omega is a 0-rank tensor, that means a function, then the lead derivative on the function is what we defined before. Now, for example, consider an n-dimensional Riemannian space, Bn with metric tensor Gij. Then the one PPT is called a motion of Vn. The generator of the one-parametric point transformation will be called a motion of Vn, if and only if the line element is invariant under the action of the one-parametric point transformation. Equivalent, indeed. The Lie derivative of the metric tensor Gij with respect to the infinitesimal generator Xi of that is 0. So Lie derivative of Gij to be 0. The point transformation which are motion of En form a group named the group of motions. And since Gij is symmetric, the condition symmetry can be expressed in this form where question mark, this Greek question mark, it indicates covariant derivative. This equation is known as the Killing equation, and Xi is called an isometry, the generator of the transformation, or Killing vector. The Killing vectors of a metric form a Lie algebra, which is called the Lie algebra. Motions are important in physics and in our real world, our Newtonian world. For instance, the Euclidean space admits as motions the group of translations and the group of rotations, and this implies the conservation of linear and angular momentum, respectively. But you can see that the world that we live, the world that we are surrounded with, it's almost Newtonian. I mean, in small scales, in the scales that we are living. I mean, we are working, we talk now. So either if you hold an object and you can rotate the object, you can change the object from the one side of your desk to the other, then that object will be the same. It will have the same length. And either if you rotate it, either if you move it, it has the same length, the same mass, it has the same property. It's the same thing. So that is due actually to the existence of this translation and rotation group of these isometries for the Euclidean space. This is not necessarily true in non-flat spaces where small rotations or small translations does not leave invariant the shape or the mass or the shape or the identity of the objects, the structure of the objects. Okay. Now, regarding the Killing algebra, the maximum dimension of the Killing algebra of a Riemannian manifold Vn is given by the following theorem. If an n-dimensional Riemannian space Vn admits a Killing algebra G Kv, then the dimension of the G of the Killing algebra is 0, is between the value 0 or n plus 1 over 2. The case where the G is equal to 1 over 2n n plus 1 is the case of a maximal symmetric space. Maximal symmetric spaces is a flat space, but it's not a unique maximal symmetric space. Another maximal symmetric space is, the Minkowski space, as I have here, is a flat space also. But the surface on a sphere, of a sphere, or of a hyperbolic plane, these are also maximal symmetric spaces. Another special class of isometries are what we call the gradient isometries. A gradient isometry has a property, it has a following property, and actually there exists a function S so that the Sk to provide us with a gradient symmetry, the first derivative of the function. When a gradient Killing vector exists, we know that the space is decomposable at this point. I mean, you can separate it and you can have an independent direction in the space. You can define that coordinate system. Maximal symmetric spaces with a gradient isometry are only the flat space. And then, since it's a flat space, you will have n, if the space has dimension n, you will have n independent directions and gradient Killing vectors. Rotations are not gradient Killing vectors, but the translations are the unique gradient Killing vectors of the flat space. Now, We define the concept of symmetries in the case of functions or in the case of geometric objects. So we can now define it in the case of differential equations. And a differential equation or a system of differential equation, it's nothing else than a function or a vector field in the Z space. So assume the differential equation H, where now I will use the mathematical notation Y to be the dependent variable and X to be the independent variable. Now I have a function H which depends on X, Y, Y prime, independent to derivative to the higher order derivative when n equal greater to 1. And we have, if we have a transformation in the space X and Y, we have to transformation. This is a generator with component C and eta. We have to extend the transformation in the Z space where the function H lives, where the differential equation lives. So we have to see how, if we have in the base manifold in the point x and p with coordinates x and y, the transformation, then we should define how this transformation is extended in the Z space. Now, for the first prolongation, this is the first extension. It's called extension or prolongation. This is the nth extension and prolongation. So what we do is, okay, we take the first prolongation and we have a first derivative. This actually will be the derivative of the previous one. So we replace dy over dx, we replace with this constant. We replace it, we write the derivatives. The derivatives are expressed like this, and we expand the Taylor, we perform a Taylor expansion in terms of epsilon to be close to 0, and the eta 1 is given by this explicit expression. Is defined by the derivatives of eta and c for the definition of the transformation in the base manifold. Similarly, the eta n is given by this rule. We can prove it very easily as we apply this approach that the procedure is here I should have n minus 1. So now, finally, we can say that the extension of the infinitesimal generator in the Z space Bn is given by this expression. The field X is called the nth prolongation of the generator, where X is the generator of the transformation in the base manifold. And it's possible to write the prolongation coefficients in terms of the partial derivatives of the components C and eta. So we can express the first derivatives. Eta and C are functions now of X and Y. So this is a total derivatives. We'll have partial derivatives. So express the eta 1 and eta 2 and 3 in terms of the first derivatives for the first and second prolongations. As you can see, this is the eta 1 and this is the eta 2. A comma denotes partial derivative with respect to the variable x and y. Now, some important observations for the prolongations are that eta n is linear in yn. So, as eta n is linear in the higher order derivative. Eta n is a polynomial in the derivatives whose coefficients are linear homogeneous in the functions c eta up to nth order partial derivatives. Now consider the differential equation. Then the equation is invariant under the action of the one parameter point transformation we generate on the vector field x if and only if the nth prolongation of x on the function h in the Z space is equal 0, or the derivative of x on h to be equal 0. This is the same definition. For second order differential equations of this form, the symmetry conditions read as the following equation. The second prolongation to be equal with omega xc, omega y eta. This is the application of the x on omega, plus the first prolongation on here on omega. So this has a derivative with the prime, with the first derivative. Now, for the free particle, where we have a specific function for omega, the symmetry condition, as we express it, is given by this form. This is a polynomial function, and we impose that the y2 is equal 0. So this is getting 0. This is a polynomial function, and as a polynomial function, it means that it's 0 if and only if each component of the polynomials are 0, if coefficients of the polynomial, of the monomials. So from here, from this equation, we construct algebraic equation. Now we construct a system of partial linear system of partial differential equations. So the solution of the system provide us with the symmetry vectors, with the vector field eta and xi, and the generator, which keep invariant the equation for the free particle. Now this system, we solve it, and we can solve it easily, and the solution of it is this generic vector field, where we have 8 independent constants, A1, A2, A3, A4, A5, A6, A7, A8. That means that this is a multi-parameter point transformations with 8 different vector fields, and we can construct a base of dimension 8 for the symmetries of the free particle. This is actually, this number of 8 is the maximum number that the second order differential equation is the maximum number of symmetries as a second order differential equations of this form OD cannot meet. Now, which are the symmetries of this? Some of them we can recognize. For instance, for A1, we define the following system. For where it follows that x equal, this is a point transformations that given by this, is a point transformation given by the symmetry vector with A1. And this is nothing else than the translation in time. So we know that the free particle is invariant the translation in time. So this is actually the way we prove it. On the other hand, from the vector field A7, we can define the system of this form, and this is a transformation. This is nothing else than the Galilean boost. So as you can see here, we were able to find what we know. All these symmetries form also the Galilean symmetries for the free particle. There are some extra transformations that we have, like the A5, which is a nonlinear. We have the A3, which is also nonlinear transformation. This transformation, or the A4, which is linear, but on theta, this should be theta x, I'm sorry. So these transformations are actually called projective transformations since they transform the geodesic equations of the free particle of the Euclidean space into geodesic equations. So they keep invariant the trajectories, the solution of the trajectory space. Now, I will go in more examples to show how we can apply them, since, okay, we define them, but the concept is to work with them, to not only to understand the physics behind them, but to work with them in order to have applications and to see how we can use them and get important information. Now, consider the symmetries of the equation, of this equation. It's a second order differential equation, nonlinear. And this equation is called Ermakov-Biney equation. It has a linear term, which is an oscillator term, and it has a non-linear term, 1 over y cubed, the Markov equation. Now, if we calculate, we apply the theory of before, we apply this formula, we can calculate the Lie symmetries. And for omega equals 0, we find that the Lie symmetries are these are three vector fields, while for omega non-zero, they will have again three symmetries with expressions like that. However, we observe if we study the structure of the algebras of this three-dimensional algebra, if we study the commutators and determine the structure constants, we observe that the algebras are exactly the same. This algebra is known as the SL2R algebra. So, for instance, when equal, and actually there exists a change of variables from xy to xy capital, for instance, as I have it here, where the one algebra, the one representation of the algebra can be written in the other representation. So we can transform the different representations of the algebras. Will not only transform the different representations of the algebras, but this transformation will relate the differential equations between the two different representations. For instance, since the one representation is for omega equals 0, and the other representation for omega non-zero, it means that if we start from the equation with non-zero, then if we apply change variables, we can eliminate the term with the oscillator term, the omega term, and to end to a nonlinear differential equations without the linear term. Indeed, for instance, when omega equals 1, the transformation from xy to x capital Y capital is given by this. And equation 1, the first equation with the oscillator term, can be expressed in terms of the later equation. So if we have the solution of the one, by applying the transformation, we can find the solution of the other one. These two equations are related through a change of variables. And this change of variables is a projective transformation, and it's a transformation which relates the two different representations for the admitted Lie algebra. This is actually a very important characteristic of the theory of symmetries of differential equations, of Lie's theory, since it can be used to represent and classify different various differential equations which have actually which are invariant under the same group of transformations. Not in the same representation, but under the same group. Now, if we want to do the calculation step by step, we start from, we apply this transformation and we employ the chain rule. So the first derivative will be this, the second derivative will be expressed like that. We change, now we replace the y, from y small y capital, and we end it with this. We collect the terms, each term is given by that, hence we end it to that equation, so this is 0. This is a proof that this transformation transforms the Markov-Pini equation with oscillator to the Markov-Pini without oscillator. Now, similar to the symmetries of functions, for a symmetry of a differential equation, we can construct the following Lagrange system. And from this system to calculate not now only the zero-order invariants, but the high-order invariant. The zero, the third, depends on the nature of the equation. The invariant function can be used to simplify the differential equations in a similar way that we can simplify a function. In the case of ODEs, the Lie invariants are applied to reduce the order of the ODE, while in the case of PDEs, the Lie invariants are used to reduce the number of independent variables. Now, let's go again to the Kepler-Coulomb equation, which is the second order differential equation of this form, which admits the Lie symmetries. We calculate the Lie symmetries. That means two Lie symmetries. The variation in time, the equation is varying in time, and it has another one symmetry, which is a scaling symmetry, is this one. And we saw before, as you can see, this is the 3/2 is nothing else than the 3/2, the ratio of the Kepler's third law. So as you can see, there is the ratio is related to the admitted symmetry. From the autonomous symmetry, we can construct the following invariants. W0 is a zero-order invariant, W1 to be the first-order derivative. By assuming the W0 to be the new independent variable and W1 the new independent variable, so we want to express the differential equation in terms of the invariants. We want to remove x and y, x, y, so we express everything in terms of W0, W1. So this, the equation, the new equation is written, the second order differential equation is reduced to a first order differential equation, or this one. And this one can be integrated very easily. Now, from here, we integrate and we replace W1 to be the first order derivative and W0 to be y, and we end with nothing else than the conservation law of energy for the Kepler-Coulomb equation. So we were able to construct the conservation law of energy by using the invariant functions for the Kepler-Coulomb equation. Now, if we use the scaling symmetry, we'll calculate the invariant Q0, yx minus 2/3, and Q1, x 1/3 dy dz. As you can see, if we take this to Q0 to be as constant, this gives us actually the Kepler's law. Now, Kepler's equation under the application of these invariants leads to the following differential equation, which is an Abel class B equation with closed form expression. Now, let us extend the analysis for the following system, for the following high order, third order differential equation, nonlinear differential equation. This equation admits also two symmetries, admits the translation in time, the in x, which is since it is autonomous, and admits another scaling symmetry. We perform reduction with respect to the first vector field to the theta hex. Then we found, as before, the invariants to be the same. Since the symmetry is the same, the invariants are W0, W1. And the differential equation is expressed in this is reduced to the second order differential equation. Now, we investigate, we want to proceed and to solve this, the new equation, which, as you can see, it is nonlinear, again, as before, and actually is non-autonomous. So the translation in time, W0, the translation of the independent variable will not be a symmetry. So the later equation, however, admits another symmetry vector. The W0 theta W0 plus 4/3 W1 theta W1, which is actually the previous scaling symmetry. This is nothing else than the scaling symmetry transformed and extended the first jet in the first the first extension, the first prolongation in the jet space. Now we can use this symmetry to reduce the equation, and the reduction of these give us a first order ODE of this form, where this is x and y are the new invariants, first order and zero order invariants with respect to the symmetry vector W0 and W1. So as you can see, we had a third order differential equation, and by applying two symmetries, one, and then the second one, we were able to reduce the equation to a first order ODE. And of course, to try to construct the solution of the equation. Now, the important here is that someone will say, okay, we start from the theta x, and then we apply the second symmetry. What will happen if we started from the from the second symmetry, from the scaling symmetry? Then we will see, I don't have the example here, but if we are starting from the second symmetry, then we will see that the reduced second order differential equation does not admit as a symmetry the extension of theta x. So we will not be able to reduce further the equation. There's a strategy and there's a theorem which states how we can proceed and when a symmetry is preserved in the reduction. So when we have a differential equation and we apply a symmetry to reduce the equation, we end with a new differential equation. Now, not all symmetries of the original equation are transformed to the new equation, while the new equation can admit extra symmetries. So the symmetries which are transformed, which remain symmetries for the reduced equation, they should have a property. Now, and in case the generators, for instance, form an abelian algebra, then the reduction preserves the Lie symmetries in any case. Since the reduced equation is different from the original equation, it is possible the reduced equation to admit extra symmetries, which are not Lie symmetries of the original equation. These new Lie symmetries have been named as type 2 hidden symmetries. And these two type 2 hidden symmetries are important since can be used to reduce further and continue the reduction of the equation. An important, I will move now from, and I would like to present you some basic elements of Noether's theorem. And an important quantity in physics, important principle in physics, in physical science, is the variation principle. And in analytical mechanics, we try to describe the equations, motions of particles or the dynamical systems by using Lagrangian functions, or the Hamiltonian form as a Hamiltonian function, such that the equations of motions to follow from the variation of the Lagrangian. The Lagrangian, it's a function which describes the dynamical system. Since I focus on physical systems where we have second order differential equations, I will focus only on Lagrangian's functions with only first derivatives. The equations of motions for the Lagrangian of the dynamical system follow from the action of the Euler-Lagrange vector field on the Lagrangian L by this, where the Euler-Lagrange vector is defined by this expression. If the Lagrangian is invariant under the action of a transformation, then it's easy to observe that the Euler-Lagrange equations are invariant under the transformation. Noether proved that if the action of a one-parameter point transformation leaves invariant the Euler-Lagrange equation, then there exists a conserved quantity corresponding to the point transformation. This Noether's theorem is actually provides us a systematic way to construct conservation laws by using, provides us a formula to construct conservation laws from the symmetry vectors which have the property to leave invariant the variation principle. Now, when a transformation leaves invariant the variation principle, if X be a generator of a one-parameter point transformation, then if there exists a function f such that the first, since I work on the Lagrange, is a function of the first derivative. The first prolongation of X on L plus L with dx dx to be equal, this component to be equal with the total derivative, then, if this condition is true, we can say that the vector field X is Noether's symmetry for the Lagrangian L. Function f in the literature in physics usually is referred as a gauge function, but this is wrong. It's a wrong terminology. Function f is a boundary term. It's a boundary term inside interaction, which does not contribute in the variation. So if we have a transformation that transforms the Lagrangian to its form plus to the same Lagrangian equal plus a boundary term, then we get the variation of it will give us the same field equations. This equation, this condition is called Noether's first theorem, and it's valid not only for point transformation, but it's valid and for generalized transformations of high order. Now, Noether's second theorem relates any Noether point symmetry to a function phi. It's important to say that if the variation is invariant under the x, this means that the equation of motions will be invariant under the x. So x, it's a Lie symmetry. It's a symmetry of the differential equation that described by the Lagrangian L. So the Noether symmetries for a subgroup on the Lie symmetries for the original dynamical system. Not all Lie symmetries are Noether symmetries, but all Noether symmetries should be Lie symmetries. For any Noether point symmetry, there corresponds the function phi, which is given by this formula, and this is the most easiest way to construct a conservation law by using a point transformation, a symmetry vector. Now, the function is a conservation law, and another symmetry leaves the differential equation invariant, it's also Lie symmetry. Then x, the Lie symmetry, or the Noether symmetry, sorry, on phi, it's equal 0. That means that the Noether integrals are invariant functions of Noether symmetry vector x. The existence of the number of Noether symmetries characterize a dynamical system. If a dynamical system of n degrees of freedom admits at least n linear independent first integrals which are in involution, where now this is the Poisson bracket, then the solution of the dynamical system can be obtained by quadratures. It means that we have n linear independent first integrals, we can express the original system of second order differential equations to an equivalent system of first order differential equations and to solve it by using quadratures. For the free particle and for the Lagrangian of this Lagrangian, recall that the free particle we can derive it from many Lagrangians, but this is the usual Lagrangian we consider in physical science to define the kinetic energy. The application of Noether's first theorem tells us that this Lagrangian admits 5 Noether symmetries. Remember that this Lagrangian admits 8 Lie symmetries. The 5 of them are Noether symmetries. This is the corresponding function f, and the corresponding Noetherian conservation law is following one. As you can see, A1, if we take only the coefficient A1, this is nothing else than the conservation law of energy. A2 is nothing else than the conservation law of momentum. And this is a Galilean boost, and these are generalized symmetries. Now, these are the conservation laws expressed in this form. And as you can see, this is the conservation law of momentum. The conservation law of momentum is given by A2, and A2 is a conservation law of the translation. So it is the momentum is related to the translation of the space. Now, if we go now to the free part, to the oscillator, and we apply the same condition. So let us determine the Noether symmetries for the oscillator with Lagrangian L. For this Lagrangian, we determine five Noether symmetries, which are the following one. This is the corresponding H function, and these are the 5 conservation laws. As you can see, I1 is nothing else than the conservation law of energy, which is related to the variance of the system in terms of time, in the change of time. However, we have another 2 sets of conservation laws, the I2 and I3, I4, I5. And we will see later in the following slide that these I2 and I3 are the analog of the Galilean boost for the oscillator. Now, as you can see, if we do the calculation, either for the, I didn't present the Lie symmetries for the oscillator, but as you can see, the Noether symmetries are 5 for the Lagrangian of the free particle and are 5 for the Lagrangian for the oscillator. They form actually, we calculate the algebra of the symmetries and we find that they have the same algebra. The symmetries, the Lie symmetries have the same algebra too, but let's focus now on the symmetry. So since they form the same algebra, the 2 different sets, it means that there should be a change of variables, so to represent the one to another. So by applying the change of variables, this change of variables in the oscillator for omega equal 1, then the chain rule, we apply the chain rule, we end to this equation. So this, by applying the transformation which relates the 2 different representations of the same algebra of the Noether theorems, Noether symmetries for the 2 equations, we were able to write the oscillator in terms of the free particle and express the solution of the oscillator in terms of the free particle. Now, as before, this is the same transformation as before. This is, we presented before, this Markov-Pini equation give us this one. So thank you a lot for your time. In the next 10 days, in the following 10 days, I will continue with applications of the symmetries in the case of PDEs. I will discuss the reduction of the dependent variables there and the derivation of type 2 symmetries, of hidden symmetries. We present some simple applications and essential applications of the symmetry analysis in fluid dynamics. Then I will discuss applications of symmetries for the solution of the Schrödinger equation and how they are related. They have the common with another symmetries of the classical Lagrangian. Then I will show you some simple applications of symmetry analysis for the solution of systems general relativity. And I will discuss a little bit how the new techniques like AI or neural networks can help us with the symmetry analysis of the differential equations. Recall that is a tool. It is a method to study dynamical systems and either to construct conservation laws, either to solve the dynamical systems, or later we can do application of physics. So I will be happy if you have any question on it. Please let me know if you have any question. I don't see anything. Okay. I assume that there's no any question, so I will just thank you all for participating. There is something. Okay, thank you. Okay. So thank you for participating. I hope to see you in 10 days. And if you have any question in general, I mean in the subject or any problem that you would like to discuss, you can send me an email. My mail is, you can find it online easily. Thank you a lot. Have a nice day.